The shop was already dark when the tow truck dropped it off. A 2013 Ford Escape with the 2.0 EcoBoost, 118,000 miles on the clock, and a note taped to the steering wheel that said, "Burns a quart every 900 miles, 3 shops can't fix it." The owner had already spent $2,300 chasing it. New valve stem seals at one shop, a PCV valve at another, the wrong one, an aftermarket unit that didn't match the calibrated orifice size Ford specified, and a compression test at a third shop that came back perfect on all 4 cylinders, which is exactly why they told her the engine was fine, and she should just keep topping it off. The engine wasn't fine. The engine was being slowly strangled by a $15 valve that nobody had actually tested, because almost nobody knows how to test it. That valve is the positive crankcase ventilation valve, the PCV valve, and when it stops working the way the engineer intended, your crankcase turns into a pressure vessel, and your engine starts drinking oil through seals that were never designed to hold back pressure from the wrong direction. Here's what nobody tells you. An engine that burns oil after 100,000 miles usually doesn't have worn rings. It has a ventilation problem, and the difference between those two diagnoses is about $4,000. Let me back up, because you need to understand what's actually happening inside your engine block right now. While it's sitting in the driveway getting ready for tomorrow's commute, combustion is not a perfect seal. It never has been. When the spark plug fires and that mixture detonates in the combustion chamber, you get somewhere north of 1,000 psi pushing down on the piston crown. Underneath that piston, you've got 3 piston rings, 2 compression rings, and an oil control ring, riding in machined grooves, pressing outward against the cylinder wall. Those rings are good. They're not perfect. Roughly 1 to 2% of that combustion pressure squeezes past them and goes down into the crankcase. That's called blow-by, and every engine ever built does it. A brand new engine off the assembly line does it. Your grandfather's flathead did it. What's in that blow-by is the problem. It's not clean air. It's unburned fuel, water vapor, carbon particulate, nitrogen oxides, sulfur compounds, and raw combustion acids. All of that gets pushed down into the sump where your oil lives. And if it just sits there, 3 things happen fast. The water vapor condenses and emulsifies with the oil, turning it into that milky sludge you see on the underside of an oil cap. The acids attack your bearing surfaces, specifically the copper and lead in the bearing overlay, and the pressure builds. That last one is what we're chasing today. Pressure builds. Before 1961, engines handled this with a road draft tube. It was exactly what it sounds like, a pipe that ran from the crankcase down toward the road surface, and as the car moved forward, airflow across the bottom of that tube created a slight low-pressure zone that sucked the vapors out and vented them into the atmosphere. Crude, but functional. It also meant every car on the road was dribbling a fine mist of oil and hydrocarbons onto the pavement all day, every day. California noticed. In 1961, the California Motor Vehicle Pollution Control Board mandated positive crankcase ventilation on all new passenger cars sold in the state. It became a federal requirement for the 1964 model year. That was the first automotive emissions device ever legally required in the United States, and it predates the catalytic converter by more than a decade, which tells you something about how significant crankcase vapors were to overall vehicle emissions. The engineering fix was elegant. Instead of dumping the vapors overboard, you route them back into the intake manifold and burn them. The intake manifold on a running engine at idle is under significant vacuum, usually somewhere between 17 and 22 inches of mercury on a healthy engine. That vacuum becomes your pump. You put a hose from the valve cover to the intake manifold, and manifold vacuum pulls the crankcase vapors up and into the combustion chamber, where they get burned along with the fresh charge. On the other side of the engine, you run a breather hose from the opposite valve cover to the clean side of the air filter housing, so filtered fresh air gets drawn in to replace what's being pulled out. Continuous scavenging. The crankcase gets flushed with clean air the entire time the engine runs. But you can't just connect a plain hose from your crankcase to your intake manifold. If you did, at idle, that 20 inches of vacuum would try to pull the crankcase into a hard vacuum, and it would suck oil straight up out of the sump and into the cylinders. You'd also be dumping a massive, uncontrolled vacuum leak into the intake tract, which would wreck your idle mixture. And at wide-open throttle, when manifold vacuum drops to almost nothing and blow-by is at its absolute peak, that plain hose would have no vacuum available to move anything at all. So the engineers put a metered check valve in that line. That's the PCV valve. And this is where it gets weird because the PCV valve is not a simple check valve. It's a variable orifice, vacuum-modulated, spring-loaded metering device that changes flow rate based on engine load, and it also functions as a flame arrestor. Inside the body of a conventional PCV valve is a tapered pintle, a shaped plunger, held in position by a calibrated spring. At high manifold vacuum, meaning idle or deceleration, the vacuum pulls the pintle up against the spring toward the seat, which narrows the flow path down to a small orifice. Low flow, just enough to keep the crankcase scavenged without destabilizing the idle mixture. Under moderate cruise vacuum, the pintle sits in the middle of its travel and the orifice opens up. Higher flow, matching the higher blow-by rate. And at wide open throttle, when manifold vacuum collapses to near zero, the spring pushes the pintle fully open to maximum flow area. And at that point, the crankcase vents through the valve into the manifold using the small remaining pressure differential and the positive pressure the crankcase itself is generating. There's one more job. If the engine backfires, if you get a flame front propagating backward through the intake manifold, that pintle slams shut against its seat instantly from the pressure pulse. It seals the crankcase off from the flame. Without that, a backfire would ignite the fuel vapor and oil mist inside your crankcase, and you'd blow the oil pan gasket or the dipstick tube or the valve cover right off the engine. This has happened. I've seen the aftermath twice, both on carbureted engines with the PCV valve deleted by someone who thought it was just an emissions restriction. Now, here's the failure mode. That pintle and that seat live in a stream of hot, oil-laden, carbon-loaded vapor for the entire life of the engine. Every hour of runtime, more residue deposits on the pintle and inside the valve body. On engines that run short trips and never fully reach operating temperature, it's worse because the water vapor never boils off, and you get an emulsified sludge that plates onto everything. On direct injection engines, it's worse still because the blow-by has a higher soot content. GDI engines run higher cylinder pressures and produce measurably more particulate. On turbocharged engines, it's worse again, because boost pressure past the rings during a load event drives blow-by rates up by a factor of 2 or 3 compared to naturally aspirated. Eventually, one of two things happens. Either the pintle gums up and sticks closed, or the deposits build up until the flow area is choked down to a fraction of spec, even with the pintle in the open position. Either way, the result is identical. The crankcase stops venting, and now the pressure has nowhere to go. Blow-by keeps arriving. 1 to 2% of every combustion event, several thousand times per minute, pushing gas past the rings into a sealed box. The crankcase should sit at slight negative pressure. A healthy engine runs somewhere between 1 and 6 inches of water column below atmospheric. When the PCV valve blocks, that flips. You go positive. And on a worn engine with a fully blocked valve, I've measured over 20 inches of water column of positive pressure. That doesn't sound like much. 20 inches of water column is less than 1 psi. But the seals in your engine weren't designed to resist pressure from the inside. They were designed to keep oil in when the pressure differential across them was 0 or slightly negative. Now you're pushing on them continuously from the wrong side for thousands of hours. Here's what fails. And here's the order it fails in. First, the valve stem seals. These are the small elastomer seals that ride on the valve guide boss at the top of the cylinder head, wiping oil off the intake and exhaust valve stems as they reciprocate. On the intake side, those valve stems have manifold vacuum on one side and pressurized, oil-saturated crankcase vapor on the other. That's the exact pressure differential that pulls oil past a marginal seal. And now, your engine is drawing oil directly into the intake port on every intake stroke, where it goes straight into the combustion chamber and gets burned. This is why the compression test on that escape came back perfect. Compression tests measure ring and valve sealing under cranking pressure. A valve stem seal leaks under vacuum on a running engine at operating temperature. A compression test will never find it. Neither will a leak-down test in most cases, because leak-down pressurizes the cylinder. Again, the wrong direction. 3 shops ran the wrong tests and got the answer their tests were designed to give. The signature of valve stem seal oil consumption is specific. You get a puff of blue smoke on cold startup because the engine sat overnight and oil seeped down the valve stems into the chamber. You get a puff of blue smoke after coasting down a long grade with your foot off the throttle because deceleration produces the highest manifold vacuum your engine will ever see, 25 inches or more, and it's sucking hard on those seals with no fuel flow to mask it, and you burn oil at a rate that seems disconnected from how you drive. Second thing that fails, the rear main seal. This is the big one, the one that costs money. The rear main is the seal around the crankshaft flange at the back of the block, sandwiched between the engine and the transmission. When crankcase pressure goes positive, it pushes oil radially outward against that seal lip continuously. The lip is designed to be held against the crank journal by a garter spring and by the pressure differential. Reverse the differential, and you're actively lifting the lip off the shaft. The bill on that job runs $200 to $2,000 on most front-wheel drive transverse engines, because you have to pull the transmission to get to it. And here's the part that makes me want to put my head through a wall. If you replace the rear main seal without fixing the PCV system, the new seal will leak too, sometimes within 6 months. I've seen the same car come back twice. Third, the front crankshaft seal behind the harmonic balancer. Fourth, valve cover gaskets, which will start weeping down the back of the head onto the exhaust manifold. And that's where the burning oil smell in the cabin comes from. Fifth, and this is the one that surprises people, the dipstick tube. On a badly blocked system, positive crankcase pressure will push the dipstick partially out of the tube. If you pop your hood and the dipstick is sitting up 1.5 inches out of its seat with oil residue around the tube, you don't have a dipstick problem. You have a ventilation problem, and it's been going on for a while. Do the math on that escape. Rear main seal, 1,600. Valve stem seals, which on that engine means pulling the cylinder head or doing the rope trick with the head on. Call it $900 to $1,400. Valve cover gasket, $250. Add the $300 she'd already spent. You're looking at over $5,000 in repairs downstream of a valve that costs somewhere between $11 and $30 depending on your engine. The dealer's not going to mention this. And I want to be careful here, because I'm not accusing anyone of fraud. Most of the time it's not fraud, it's flat rate labor. A tech gets paid by book time, and the book time on diagnose oil consumption is a fraction of what he'd actually need to test crankcase pressure properly, source the manometer, verify PCV flow, and check the fresh air side of the circuit. But the book time on replace rear main seal is 6.4 hours, and that pays. The incentive structure doesn't reward finding a $15 valve. It rewards replacing an assembly. There's a second reason this gets missed, and it's a technology shift most people haven't caught up to. The classic Pintle spring PCV valve that everyone pictures, the little metal or plastic canister that rattles when you shake it, is disappearing. It's still on plenty of naturally aspirated engines, but since roughly 2005, manufacturers have been moving toward integrated crankcase ventilation systems where the pressure regulation is built into the valve cover itself, and there's no serviceable valve at all. BMW led this with the cyclonic oil separator systems on the N54 and N55, where the entire assembly is bonded into the plastic valve cover and includes a diaphragm-based pressure regulating valve. When that diaphragm tears, and on the N54 it tears, usually somewhere between 80,000 and 120,000 miles, the intake manifold vacuum gets a direct, unrestricted path to the crankcase. Instead of positive pressure, you get excessive negative pressure, which is the opposite failure, but produces the same oil consumption because now you're actively sucking oil past the valve stem seals, and the oil separator can't keep up. The tell on those is a whistling sound at idle and in cold weather, a collapsed oil filler cap, or a deformed dipstick tube. Volkswagen and Audi did the same thing on the 2.0 TSI with the EA888 engine family. The PCV assembly is bolted to the valve cover, contains a spring-loaded diaphragm, and when it fails, you get a lean code, a rough idle, and oil consumption that owners in forums have documented at a quart per 700 miles. Audi extended warranty coverage on some of these. There are multiple TSBs across the platform addressing revised PCV assemblies with updated part numbers, and the fact that a part gets revised 3 times in 8 years tells you the first design didn't work. Toyota went a different route on a lot of their engines. The 2AZFE, the 2GRFE, the 2ZRFE, conventional serviceable PCV valve, threaded or press fit into the valve cover, replaceable in 5 minutes with a socket. Honda does something similar on the K-Series and R-Series, which is why, in general, a Camry or an Accord with 180,000 miles is less likely to be burning a quart every 800 miles than a comparable European car. Not because the engine is inherently better, but because the ventilation system is serviceable, and somebody probably serviced it at some point by accident during another job. But Toyota's not immune, and there's a wrinkle on the 2AZFE specifically that's worth knowing. That engine had a documented oil consumption issue that Toyota addressed with a warranty enhancement program, and the fix involved revised piston assemblies with redesigned oil ring geometry. The oil control rings were getting coked up and losing their ability to scrape. Now here's the connection nobody makes. Coked oil control rings and a restricted PCV system feed each other. Restricted ventilation means more blow-by contaminants staying in the oil, which means faster oil degradation, which means more deposits in the ring lands, which means the oil control ring sticks in its groove, which means more oil in the chamber and more blow-by past the rings, which means more crankcase pressure. It's a loop. Once it starts, it accelerates. Which brings me back to the thing I said at the top about worn rings. When a shop tells you the engine's worn out, it's burning oil, that's just a high-mileage engine, what they usually mean is they don't want to spend 2 hours diagnosing it. And in fairness, sometimes the rings really are shot. But in my experience, and this is 14 years in an independent shop plus 6 as an insurance inspector looking at engines people were trying to get paid out on, the ratio is something like 4-to-1. 4 ventilation-driven oil consumption cases for every one genuinely worn-out set of rings. And most of the ring failures I did find were secondary. The rings coked up because the oil was cooking, and the oil was cooking because the crankcase wasn't venting. This isn't theory. You can test it in your driveway in about 20 minutes. Let's start with finding the thing. Because on half the cars I've worked on, the owner had never seen it and didn't know it existed. Open the hood and look at your valve covers. You're looking for 2 hoses coming off the top of the engine that don't go to the cooling system and don't carry fuel. One of them goes from a valve cover to the intake manifold. That's the PCV side, the dirty side, the vacuum side. The other goes from the opposite valve cover, or the opposite end of the same valve cover, to the intake tube between the air filter and the throttle body. That's the fresh air breather side, the clean side. The PCV valve itself sits on the manifold end of that first hose in some designs, and on the valve cover end in others. On most Toyota 4-cylinders, it's threaded into the valve cover near the front, a small metal or plastic nub with a hose clamped over it, and it backs out with a 22mm or 24mm wrench. On GM small blocks and a lot of the older domestic V8s, it's a rubber grommet in the valve cover, and the valve just pulls straight out with a firm twist. On the Ford Modular V8, it's usually on the back of the intake manifold on the passenger side, and you'll need to get your hand down behind there. On Subaru Boxer engines, it's near the back of the intake manifold, and you'll be swearing at it. If you can't find one, look up your specific engine, because there's a real chance you have one of the integrated systems and there is no serviceable valve, in which case the diagnostic is the same, but the fix is a valve cover assembly instead of a $15 part. Now, let's test it. And I'm going to give you 3 tests, from the crudest to the most definitive, because most people are going to stop after the first one, and I want the first one to at least be useful. Test 1, the shake test. Pull the valve out of the valve cover with the engine off. Shake it next to your ear. A conventional PCV valve should rattle. That's the pintle moving freely in the bore. If it's silent, the pintle is stuck and the valve is dead. Replace it. But understand the limitation, and this is where a lot of the internet advice fails you. A valve can rattle perfectly and still be restricted. The pintle can be free while the flow area around it is choked down with carbon. A rattle proves the pintle moves. It doesn't prove the valve flows. I've pulled valves that rattled like a maraca and had an orifice so coked I couldn't see light through them. Test 2, the vacuum test. Engine warm, idling, parking brake on. Pull the PCV valve out of the valve cover grommet, but leave it connected to its hose so it's still under manifold vacuum. Put your thumb over the open end. You should feel strong, steady suction. enough that it's uncomfortable to hold, and when you seal it off, the engine idle should change noticeably, usually dropping 50 to 100 RPM, because you just eliminated a metered air path into the manifold. If there's no suction, either the valve is blocked, or the hose is collapsed or split, or there's a plugged port in the manifold. Check the hose first. PCV hoses go hard and crack from the inside, and on engines over 15 years old, I replace the hose whenever I replace the valve. It's $4. If there's suction, but the idle doesn't change at all when you block it, that's a partial restriction. The valve is passing some air, but not enough to matter to the idle mixture. That's your marginal valve, the one that rattles, looks fine, and is slowly destroying your rear main seal. Test 3 is the one that actually answers the question, and it's the one nobody does. You measure crankcase pressure directly. You need a manometer. A slack tube water manometer runs about $25, or you can use a digital differential pressure gauge if you have one. Pull the dipstick out and seal the manometer hose into the dipstick tube with a rubber stopper or a wad of shop rag wrapped tight. You need it sealed, but you don't need it perfect. Start the engine. Let it come to full operating temperature because a cold engine has different blow-by characteristics and different oil viscosity, and you'll get a false reading. At warm idle on a healthy engine, you should read negative, somewhere between 1 and 6 inches of water column below atmospheric. Some manufacturers spec tighter than that, and if you can find your engine's service manual spec, use it. If you read 0, the system isn't scavenging. If you read positive, the system is blocked, and the pressure is already working on your seals. And if you read heavily negative, more than about 10 inches of water column below atmospheric, you've got the opposite problem, a stuck open valve or a torn diaphragm, and that's pulling oil past your seals just as hard, just from the other direction. Now here's the step that separates a real diagnosis from a part swap. Before you condemn the PCV valve, check the fresh air side. Everybody focuses on the PCV valve because it's the named part, but the crankcase ventilation system is a circuit, and a circuit needs an inlet and an outlet. The fresh air breather hose, the one running from the valve cover to the intake tube, has to flow, or the PCV valve on the other side has nothing to draw. That hose gets restricted the same way, with the same deposits, and on a lot of engines it has a small screen or a fixed orifice in it that plugs solid. I had a Silverado come in, 5.3 liter, 156,000 miles, burning oil and blowing the oil fill cap off the valve cover about once a month. The owner had replaced the PCV valve twice. Brand new valve, still positive crankcase pressure. The fresh air tube from the airbox to the driver's side valve cover was completely occluded with a black gelled sludge. You could not push a pencil through it. 15 minutes with a bottle brush and some brake cleaner, and the crankcase pulled negative 5 inches of water. That truck stopped burning oil. Total parts cost $0 because he'd already bought the valve he didn't need. Same principle on any engine with an oil separator or a labyrinth baffle in the valve cover. Those baffles exist to knock liquid oil out of the vapor stream before it goes to the intake, and they clog. If yours is a serviceable separator, some are, most integrated ones aren't, pull it and clean it. While you're in there, one more check. Pull the vacuum hose off the PCV valve at the manifold end and look inside the manifold port. On direct injection engines especially, that port cokes up. Carbon builds in a ring around the opening and reduces flow. A cotton swab and some intake cleaner takes care of it. Now, the replacement itself, and the part where I'm going to be a little bit of a hardliner. Buy the OEM valve. I know how that sounds. I know that's what every parts counter tries to upsell you into. But the PCV valve is a calibrated device. The spring rate and the orifice geometry are matched to your specific engine's displacement, blow-by rate, and manifold vacuum characteristics. Two valves that look physically identical and both fit your valve cover can have completely different flow curves. That's what happened on the Escape. The previous shop installed a generic valve that fit and rattled and did nothing because the calibration was wrong for a turbocharged 2.0. The price delta is usually $8 to $20. Against a rear main seal job, that's not a decision. The install on a conventional valve is genuinely 5 minutes. Engine off and cool. Pull the hose off. Unthread or twist the valve out. If it's a press fit into a rubber grommet, inspect that grommet. After 15 years, those go hard and crack, and a leaking grommet is an unmetered vacuum leak that'll throw a lean code and a rough idle. Grommets are $2. Replace it while you're there. Install the new valve. Note the flow direction. Most valves are marked, and the arrow or the manifold side end goes toward vacuum. Reconnect the hose, done. And then change your oil. Right then that same day, even if you're only halfway to your interval. Here's the reasoning. The entire time that system was blocked, contaminants were accumulating in your oil that should have been vented out. Fuel dilution, water, acids. That oil is worn out regardless of what the mileage sticker says. Get it out. And on a high mileage engine that's been running blocked, I'd shorten the next interval too. Run it 3,000 miles and dump it again. Because you're going to be flushing residue out of the sump for a while. The maintenance interval on this thing, since nobody publishes it clearly, 60,000 to 100,000 miles on a conventional serviceable PCV valve is the range I use, and I go to the short end of that if the car does mostly short trips, if it's turbocharged, or if it's direct injection. On the integrated systems, you're generally replacing the assembly when it fails rather than on a schedule. But I'd inspect crankcase pressure at every other oil change past 80,000 miles. And one thing I want to kill right here because I see it recommended constantly. Do not clean a PCV valve with carb cleaner and reuse it. You can dissolve the visible deposits, sure. You cannot restore a spring that's fatigued from 20 years of thermal cycling. And you cannot repair a pintle seat that's been eroded or a valve body that's worn oval. You'll get a valve that rattles beautifully and flows at 70% of spec, and you'll go right back to positive crankcase pressure in a few thousand miles. It's a $15 part. Let me close the loop on the Escape. I pulled the dipstick and put a manometer on it. Warm idle, positive 8 inches of water column, not subtle. The aftermarket PCV valve the previous shop installed rattled fine and had suction at the hose, which is why they thought it was good. But the flow rate was wrong for that engine, and the crankcase couldn't keep up with the blow-by a 118,000-mile Turbo 4 was producing. On top of that, the fresh air line was about 60% occluded. I put in the correct Ford valve, cleaned the fresh air passage, replaced both hoses because they were hard as conduit, changed the oil, and put the manometer back on. Negative 4 inches of water column. Now, I need to be honest about the outcome because I don't want to sell you a miracle. Her valve stem seals were already compromised. 3 years of positive crankcase pressure had done that damage, and fixing the ventilation doesn't unharden an elastomer seal. She went from a quart every 900 miles to a quart every 2,800 miles. That's a real improvement, and it's a car she can drive, but the damage that was already done was already done. That's the part I want you to sit with. If she tested crankcase pressure at 80,000 miles, 20 minutes, and a $25 manometer, the seals would still be fine. The valve would have cost her $15. Instead, she spent $2,300 on wrong repairs, and she's still topping off oil. The pattern I saw over and over doing insurance inspections was never a single catastrophic failure. It was a $5 problem that nobody checked, feeding a $50 problem, feeding a $5,000 problem over the course of about 4 years. And every single link in that chain was visible, testable, and cheap to interrupt if anybody had bothered to look. So this weekend, go find the PCV valve on your engine. Pull it, shake it, put your thumb over it at idle. If you've got 80,000 miles or more and you've never touched it, just replace it. You're not going to hurt anything, and the odds are strongly against it still being in spec. Check the fresh air side too, because that's the half everyone forgets. 20 minutes, $15. It's the highest return on investment maintenance item on your entire vehicle, and it's the one item that isn't on a single manufacturer's maintenance schedule in any meaningful way. That's not an accident either, but that's a different video.